transformations of functions. And so to do that, we need to first consider three of the parent functions that we saw earlier. So this is a quadratic function. It has that parabola shape. And if we remember, we can just do input output. So 0 squared is just 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. We do the other side. Negative 1 squared is positive 1. Negative 2 squared is positive 4. And negative 3 squared is 9. So that was that basic parabola shape, which made like a U kind of shape. Looks like this. The absolute value function, the absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. So we saw this one stays the same on the right side, and it created that linear section. But the absolute value of negative 1 is positive 1 because it's the distance away from 0. The absolute value of negative 2 is positive 2. And we created the other linear section of this absolute value function. And so it just looks like a V shape. So that's the absolute value. The square root function is a radical function. And the square root of 0 was 0. The square root of 1 was 1. There wasn't a nice point for the square root of 2. The next nice point was the square root of 4. The square root of 4 is 2. So we put a dot there. Then we're looking for the next nice square root, which is the square root of 9. So square root of 9 is 3. We can put our point there. This one went off to the right with a vertex there at 0, 0. There was nothing to the left of it because I can't square root a negative. So if we know these basic graph shapes, we can think about how do I manipulate and transform them a little bit. So a horizontal translation is going to go left or right. This affects the x values or the inputs of the function. So we want to see what does the manipulation of the equation due to the original graph or the parent function. So let's look at these in Desmos a little bit. We're going to take this equation, x minus 3 squared, and compare it to what the original graph looks like. So this is the parent function, y equals x squared. And I'm going to type in what we had, x minus 3 squared. Look what happened. It maintained the same shape, but it has shifted to the right 3. Think about where that vertex was. It was 0, 0. It's now 3, 0. So this is shifted to the right 3. We just want to take this and kind of sketch out what the new shape looks like. So this went like that. And it moved to the right 3. We can take the absolute value of x minus 5. So we're going to change this function to the absolute value of x, and then absolute value of x minus 5. The V shape stayed the same, but this one moved to the right 5. So we put this back in here as a sketch. We're not graphing a real complete version of it, but it looks like this. And we saw that it moved right 5. The last one there says the square root of x minus 7. So we're going to change the parent function again. It's the square root of x. We're going to take that square root, and inside it we're moving the x's, x minus 7. This moved our x's to the right 7. So now, if I sketch that one, it still had that square root graph shape, but it started here at 7, 0 and went off to the right. So it went right 7. X plus 2 squared. The squared tells me I'm going to have a quadratic, a x squared function. So I'm going to go back to y equals x squared. We're going to manipulate it into x plus 3 squared, x plus 2 squared. And that has moved the parabola to the left 2. So that 0, 0 is now at negative 2, 0. So we went left 2, and we're just sketching it again. Not a perfect graph. But it looks like this. If we did x plus 6 inside the absolute value, that plus 6 affects the x values. So we're still affecting our inputs. We change our absolute value of x, x plus 6. We can see it moved the original function from 0, 0 to a vertex of negative 6, 0, so it moved to the left 6. Our v is the same shape v, just moved left 6. The last one, x plus 4 inside the square root. You can have a guess of what that's going to do. We're affecting our x values. So square root of x inside the square root. We're doing x plus 4. And we move to the left 4, as expected. It doesn't change the direction or anything, so it's still going to maintain going off to the right. It just moves left 4. So what we hopefully noticed is that when you change that value inside of the function, you're affecting our inputs. So if we had y equals whatever that function is, whether it's x squared, something squared, x plus some number, x minus some number, whatever that number is moving it left or right. Now when it was plus, it moved it to the left, and when it was minus, it moved it to the right. So if I have these functions, we want to identify what is the parent function and then describe the transformation that's going to happen. So part A has g of x is 1 over x plus 8. That parent function is that 1 over x function. If you remember what that name was, it's called a rational function. It made that weird graph that had the asymptotes, so it had this shape. But what I'm going to do is take that function and move it to the left 8. The inputs are being affected. The x's are adding 8 to the x. That's inside where the x originally was. Now there's an x plus 8. That moved it to the left 8. B has a parent function of 3 to the x. It's an exponential function because we have x as an exponent. So exponential, look at what happened. The x part of it changed, the exponent. X changed to x minus 6. So we have affected the inputs, which moved it left or right. Since it's minus 6, it moved to the right 6. Now let's switch to vertical translations. Vertical translations go up and down. They're going to affect the y values, or the outputs of the function. If we look at these on Desmos, we still have, look at the main function. We have an x squared, we have an absolute value of x, we have a square root of x. So we're using those three primary functions, our parent functions that we started with. So x squared plus 2. we take that x squared graph, and then I'm going to create a new one. So y equals x squared, but plus 2. Look what happened. The original moved up 2. It shifted everything up 2. Then we had absolute value of x minus 6. So absolute value of x is the parent function. Absolute, delete all this. Absolute value of x minus 6. The minus 6 is not inside the absolute value. It's outside, so it's affecting the outputs, and it moved it down 6. Lastly, we had the square root of x, and outside of the function we have minus 7, so we are still going to affect the outputs. Let's change this to the square root again. Square root of x and square root of x outside minus 7. It moved it down 7. So each one of these either moves it up or down. We saw with the plus 2, it moved it up 2. It maintained our quadratic shape, so that part didn't change, but it did go up 2. Minus 6 made it move down 6. We still have a absolute value shape, but it goes down 6. The square root of x minus 7 moved down 7. So what was at 0, 0 now is at 0, negative 7. And it's going off to the right still, so down 7. I will make a disclaimer. For this one, it's often going to be written as negative 7 plus the square root of x to just give you this distinction that the negative 7, the minus 7 is outside of the square root. It's not inside the square root. And those are the same. So if you think about, if you have 2 minus 5, that's the same as negative 5 plus 2. So that's what's going on here. The square root of x minus 7 can be reordered to negative 7 plus the square root of x. Without a graph, we can still describe what transformations are going on. We look for what is the parent function, and in part A, it's a little bit more obvious that that's a log function. So the parent function was y equals log of x, which the name for it is logarithmic. The transformations that happened, nothing's affecting the x values, it's inside of the log, but the outputs, this minus 7, has moved the function down 7. In B, we can see a few things have happened, but when I look for the general parent function of x minus 1 cubed, that cubed tells me that the original function was x cubed. It's a cubic function, which is in that polynomial family. If we apply the transformations in a specific order, we start with the inputs. So the x values are being we're subtracting 1 from them. We see that x minus 1 affects the inputs. That's a right 1 transformation. The cube doesn't do anything as far as the transformation goes. The cube is our parent function. The plus 2 is outside of the parent function, which makes it move up 2. So a left or right is inside, up and down is outside, affecting the y values of the outputs. A reflection, there are two main ones that we think about. We look at horizontal and vertical reflections right now. So when a graph is reflected horizontally, it affects the x values. It is a reflection over the y-axis. All right, think about where your axes are. Here's our x-axis and there's our y-axis. If I take this point A and reflect horizontally, I'm reflecting it over here to make a new point. We'll call it A prime. That new point did not change its y value, but it did change its x value. So the x value is what's affected. Symbolically, that reflection would look like f of negative x. The x's are being multiplied by -1. So when you graph that, just make sure that you're thinking about which axis you are using. That y-axis is the up and down one, but it's affecting horizontal only the x values. You multiply the x values by -1. When a graph is reflected vertically, it affects the y values. And it's a reflection over the x-axis. Symbolically, that looks like negative f of x. So when we look at this first function, the square root of negative x, think about what was going on. If I had the original function f of x equals the square root of x, the inputs have now become negative x, so that was what was input into the function, negative x. We want to see what does that do to our graph. So let's go to Desmos to do that first. If we took the square root of x, we have this function. The inputs are going to be affected, and it creates this new function. Let's change the color here. Orange. We can see that the function has been reflected over the y-axis. It's reflected horizontally. So the x values have been changed. We had a point at 0, 0. That's not changing, but let's say that's 0.42. I'll just type it in here, 42. That point has been reflected, which makes that -42 over here. So the x values were multiplied by -1. If we remember what the main parent function shape looks like, it's easier to do these manipulations. So now, there's our vertex of 0, 0, and it went off in the other direction. So it reflected, but you can't just say it reflected. You have to be specific and say it reflected over the y-axis. If you only say reflection or it reflected, you'll definitely miss points on that question, or you'll miss it completely. You need to be specific as to how it reflected. Now for negative x squared, that negative is outside of the function, affecting the outputs. So look at what is going on here. If I had the original function, f of x was x squared. The new function, negative x squared, negated that f of x. So we're going to take that and put it into Desmos. The original function x squared is now negative x squared, and it's reflected over the x-axis. So that's a vertical reflection. When you have a negative in front, it's a vertical reflection. So instead of that parabola opening up, it opens down, but it still maintains those same shape of the parabola shape. So this reflected over the x-axis, we just multiply the y values by -1 if it reflects over the x-axis. If it reflected over the y-axis, it's affecting the x's, and they were multiplied by -1. So again, we're going to identify a parent function first. We don't have to know what the graph is right now. It would be good if we had an idea in our head, but we're not focused on a graph just from an equation. So this is an exponential function. I know it's exponential because I have x as an exponent. The base would be 2. Exponentials will always have a base, so it's some type of number. That 2 is not a transformation. That is the actual parent function, 2 to some power. The transformation that happened is that you have a negative x. So a negative affected the x values, or affected the inputs, which is reflecting. We just have to decide how did it reflect it. So it reflected over the y-axis if it is affecting our x's. Y-axis. In B, you can see several transformations. So this one is an absolute value function. With it being an absolute value, we know it's going to have a V shape. But there are multiple transformations going on, and we start with what happens to the x's. So the x's have +6, which makes it move to the left 6. If it's inside affecting our x's, it's left or right. So plus made it move to the left. Then we have this negative outside of the absolute value. So it's outside of the parent function, which makes it move, or not move, it's reflecting. So reflected over the x-axis. And let's just move this down here. Then lastly, there's one more transformation, this +8. The +8 makes it move up 8. So we talked about how inside plus or minus was left or right. Outside of the function, plus or minus was up or down. The last thing we have are stretches. So there are vertical stretches and there are horizontal stretches or shrinks. So vertical stretches and shrinks are happening when the output of a function is being multiplied by some constant. It will either vertically stretch or shrink depending on what that constant is, but this always affects the y values of the function. Symbolically, it would look like you have some constant that's being multiplied, that is a multiplier to the function. If that constant is bigger than 1, if k is greater than 1, it vertically stretched the function by a factor of k. You would just multiply the y coordinates by k. If it's between 0 and 1, that's a vertical shrink by a factor of k. It still multiplies the y coordinates by k, but it's shrinking them because it's smaller than 1. So we have to investigate this a little bit more graphically. 3 absolute value of x. When we had the absolute value of x function, we know it made a V shape. If I multiply that function by 3, it has stretched this function vertically. So think about that point at 1, 1 has been stretched up to a point at 1, 3. I'll put it there. So the vertical component was stretched. Whatever value we put in front, so if I put a 4, that stretched it up by 4. 2 was stretched by a factor of 2. 5, 6, whatever we're doing is vertically stretching it. So when I think about 3 absolute value of x, we just say this was a vertical stretch by a factor of 3. That by a factor of 3 is really important as well, because if you just say it was a vertical stretch, you're not explaining how it was stretched. If you don't include the word vertical, you also aren't explaining what type of stretch. So all of that is important in a complete answer. Vertical stretch by a factor of 3. Graphically, what that looked like, our V shape was stretched up more. It did not change that point 0, 0, that vertex, but it did vertically stretch each one of those y values. Now, 1/2 x squared. X squared we know makes a parabola shape, so it should be some type of quadratic. There's our parent function. If I do y equals negative x squared, it would have reflected it. We talked about a reflection already. But 1/2, this is the red one we're looking at, 1/2 has shrunk this horizontally. Not horizontally, vertically. Sorry. So keeping it the same, but 1/2 shrunk it down. It's hard to see that when you're just doing one value, so let me make a slider, and I'm going to put some values between 0 and 1. If it's currently 1, it's the same. But when I shrink it, you can start to see this vertical component shrinking. And the smaller that constant is, the more it shrinks. So let's say I go back to 1/2. So 0.5. Some of the points on a quadratic were 0, 0, 1, 1, 2, 4. So let's look at 2, 4. If I shrink this by 1/2, the y values are vertically shrunk. 4 times 1/2 is 2. So there's your coordinate. You see that vertical component shrink. One of the other ones was 3, 9. If I vertically shrink, that 9 is going to be multiplied by a factor of 1/2. 9 times 1/2 is 4.5. So we can see that vertical distance has decreased by a factor of 1/2. Alright, so take that parabola and decrease our vertical distance. So vertical shrink this time by a factor of 1/2. So if that had been a negative 1/2, let's go back to here. Get rid of all these points. Positive 1/2 we know shrunk it. Negative 1/2 would shrink and reflect over the x-axis. So those are two separate transformations that are happening at one time. And so you would list both of them. Alright, in 8, we're identifying our parent function again. So I see a square root that tells me I'm working with a square root function. It's the square root of x, which is a radical function. There are several transformations happening. Let's start with what's affecting our x values. The inputs, we're subtracting 10. X minus 10 is affecting a horizontal shift. So that goes right 10. But we also have this times 2. So the the actual parent function square root of x, that thing is being multiplied by 2. The outputs are being multiplied, which makes the y values being vertical stretch by a factor of 2. And then plus 9 is up 9. Remember, I could have reordered that to 2 square root x minus 10 and then add 9, but a lot of times we put that 9 in front so that we are clear it's not inside the square root symbol. Alright, b, we have a cubic function. It's something to the third power, so it's y equals x cubed is our parent function. A cubic was in that polynomial family. The transformations that are happening here, if we list them, go with what is affecting our x's first. We see the x plus 1. That's a left 1. Then we're multiplying by 2/3. So just like what we saw, there's 2/3 times the function. So in that case, it's a vertical shrink. By a factor of 2/3. Then lastly, we have this minus 4, so we go down 4. That's outside the function, which moves it down. So as a note, just be careful with when you're thinking about that constant in front, because if that constant is between 0 and 1, that was a vertical shrink. If it was greater than 1, it was a vertical stretch. Just because it's a fraction does not mean it's always less than 1. We can have an improper fraction, so if I had flipped that to 3/2, that's improper and bigger than 1, which would make that a vertical stretch. The last transformation we have are horizontal stretches and shrinks, and these are definitely the weirdest one. So this is when an input of a function is multiplied by a constant. It will either horizontally stretch or shrink the function. It does affect our x values. Symbolically, you're multiplying the x's by some constant, so k times x. But this one operates a little bit backwards. So if k is bigger than 1, it's a horizontal shrink. It's a shrink by a factor of 1/k. So that's the reciprocal of k. It will multiply those x coordinates by 1/k. So whatever x is, you're going to multiply by 1/that k. If your constant is between 0 and 1, it will be a horizontal stretch by a factor of 1/k. So if we looked at the difference between these, we have a parent function of square root of x and square root of 2x. Horizontally, what has happened is that each of these x values, so 1, 1 was an original x coordinate, the x value has been multiplied by 1, or 1/2. So 1/2 is 1/2, 1/k, gives you that horizontal shrink. So we had a point at 9, 3. That was an original point. If I shrink this by 1/2 horizontally, 9 times 1/2 is 4.5. And you see that same point just horizontally shrunk. So that's what's going on when there's a value bigger than 1 every single time. So let me make that k slider. Something bigger than 1 is horizontally shrinking. So even though I made it 4 like a 4x here. That has shrunk this horizontally. So we had a point at 1, 1. Horizontally, it's now at 1/4, 1. You can see that horizontal shrink. A little bit more obvious is the 16, 4 point. On the original function, we know it is at 16, 4. If I horizontally shrink that by 1/4, since it's 1 over k, we're at 4, 4. So this function is a horizontal shrink by a factor of 1/2, since it's 1 over k. K is 2, 1 over 2 is the factor. We saw that moved the function horizontally, or it shrunk the distance horizontally. It maintained the same shape. So you can't really tell a big difference if you didn't graph what the parent function was. So maybe I put in, that was our parent function. This is the transformed function. And 1/3 x squared. I'm going to take that function x squared, bring it back here. My x's are being multiplied by a constant. That has horizontally stretched this. So we had a point at 1, 1. Horizontally, it's now at 3, 1. So I'm stretching the horizontal distance by a factor of 3. You have to find whatever the constant is and multiply by the reciprocal. The reciprocal of 1 over 3 is 3 over 1. So that is a horizontal stretch. Graphically, we saw that widen our horizontal component. So we think about some parent functions in this next one. We have 2 to the 5x minus 11. 2 to the x power is our parent function. We have a base to some x power. That's an exponential function. The x values are being multiplied by a constant, so it's a horizontal stretch or shrink. We have to determine which one it is. So it's a horizontal shrink this time by a factor of 1/5. Since we're multiplying by 5, that constant is bigger than 1, so it's a horizontal shrink by a factor of 1 over 5. There is a minus 11 in this function. So that minus 11 is outside of the function, or parent function. So it is moving down 11. And then we come to this log function. So this would be log of x, which is just a logarithmic function. But there are lots of transformations going on here. The first one, we go to our x's and see what's affecting our x's. We have a 1/4. Since it's being multiplied by a constant, it is a horizontal stretch or shrink. That constant is between 0 and 1, which means we have a horizontal stretch by a factor of 4. So 1 over 4, if I do the reciprocal, becomes 4 over 1, which is just 4. If I go outside of the log, we see this minus, but that is the same as negative log of 1/4 x. And then plus 3. The 3 was positive. So it's a little easier to read it this way to know that that minus is a reflection. So we reflect over one of the axes. Since it's a negative outside of the function, it's affecting our outputs, which are our y values. So the y values are reflected over the x-axis. The plus 3 is just up 3. But it is done in a specific order. So when we think about the order matters. We follow order of operations, but we go according to the inputs first and then towards the outputs. So for example, in our transformation f of negative x plus 7, the negative x means I'm affecting the inputs first. They've been multiplied by a negative, which means it's reflecting over the y-axis first. Then you would shift up 7. So we want to make sure we describe things in order. In number 11, we have a quadratic function. Let's think about the parent function. That x squared, here's our squared. That's what told me I have a quadratic, and the x's are being manipulated. So x plus 6 inside moves left 6. Then we can work outside of the function. So outside, we see negative 2. That's actually doing two things at one time. So negative 2, let's say the 2 is a vertical stretch by a factor of 2. But the negative part is a reflection, so it reflects over the x-axis. Because both of those are happening basically at the same time, you could have put them in either order. So that one is interchangeable. But then the last thing that would happen was this down 5 component. All right, the other part of the notes are about how do I manipulate something without the actual function or parent function. It's just some mystery function.